Unit 7, Alcohol, Phenol and Ethers. You have learned that substitution of one or more hydrogen atom from a hydrocarbon by another atom or a group of atoms result in the formation of entirely new compound having altogether different properties and application. Alcohol and phenols are formed when a hydrogen atom in a hydrocarbon aliphatic and aromatic respectively is replaced by OH group. These classes of compound find wide application in industries as well as in day-to-day life. For instance, have you ever noticed that ordinary spirit used for polishing wooden furniture is chiarify a compound containing hydroxyl group ethanol? The sugar we eat, the cotton used for fabric, the paper we use for writing, as all made up of compound containing OH group. Just think of life without paper, no notebook, books, newspaper, currency note, check, certificate, etc. The magazines carrying beautiful photographs and interesting story would disappear from our life. It would have been really a different world. An alcohol contains one or more hydroxyl group directly attached to carbon atom of an aliphatic system CH3OH, while a phenol contains OH group directly attached to a carbon atom of an aromatic system C6H5OH. The substitution of a hydrogen atom in a hydrocarbon by an alkoxy or aryloxy group yields another class of compound known as ethers, for example CH3OCH3. You may also visualize ethers as compounds formed by substituting the hydrogen atom of hydroxyl group of an alcohol or phenol by an alkyl or aryl group. In this unit, we shall discuss the chemistry of three classes of compound, namely alcohol, phenol and ether. Classification. The classification of compound makes their study systematic and hence simpler. Therefore, let us first learn how are phenol, alcohol and ether classified. Alcohol, mono, di, tri and polyhydric alcohol. Alcohol and phenol may be classified as mono, di, tri or polyhydric compound depending on whether they contain 1, 2, 3 or many hydroxyl group respectively in their structure as given below. Monohydric alcohol may be further classified according to the hybridization of the carbon atom to which the hydroxyl group is attached. Compound containing CsP3 OH bond. In this case of alcohol, the OH group is attached to an sp3 hybridized carbon atom of an alkyl group. They are further classified as follow: primary, secondary and tertiary alcohol. In these three types of alcohol, the OH group is attached to primary, secondary and tertiary carbon atom respectively as depicted below. Allyl alcohol. In this alcohol, the OH group is attached to a sp3 hybridized carbon adjacent to the carbon-carbon double bond, that is to an alkylic carbon, for example, primary, secondary and tertiary. Benzylic alcohol. In this alcohol, the OH group is attached to a sp3 hybridized carbon atom next to an aromatic ring, for example, allylic and benzylic alcohol may be primary, secondary and tertiary. Compounds containing C sp2OH bond. These alcohol contain OH group bonded to a carbon-carbon double bond, that is to a vinylic carbon or an aryl carbon. These alcohol are also known as vinylic alcohol. Phenol, mono, di and trihydric phenols. Ethers are classified as simple or symmetrical if the alkyl or aryl group attached to the carbon atom are the same, and mixed or unsymmetrical if the two groups are different. Diethyl ether C2H5O C2H5 is a symmetrical ether, whereas C2H5OCH3 and C2H5OC6H5 are unsymmetrical ethers. Nomenclature. Alcohols. The common name of an alcohol is derived from the common name of alkyl group and adding the word alcohol to it. For example, CH3OH is methyl alcohol. According to IUPAC system, the name of an alcohol is derived from the name of alkane from which the alcohol is derived by substituting E of an alkane with the suffix OL. The position of substituent are indicated by numerals. For this, the longest carbon chain is numbered starting at the end nearest to the hydroxyl group. The position of the OH group and the other substituent are indicated by using the number of carbon atoms to which these are attached. For naming polyhydric alcohol, the E of alkane is retained and the ending OL is added. The number of OH group is indicated by adding the multiplicative prefix di, tri, etc. Before OL, the position of OH group are indicated by appropriate locants. Example, HO, CH2, CH2, OH is named as ethane 1,2-diol. Table 7.1 give common and IUPAC name of few alcohol as examples. Cyclic alcohol are named using the prefix cyclo and considering the OH group attached to C1. Phenols. The simplest hydroxy derivative of benzene is phenol. It is its common name and also an expected IUPAC name, as structure of phenol involve a benzene ring in its substituent compounds. The term ortho 1,2-di substituted, meta 1,3-di substituted, and para 1,4-di substituted are often used in the common names. IUPAC name. Dihydroxy derivative of benzene are known as 1,2,1,3 and 1,4 benzene diol. Ethers. Common name of ethers are derived from the name of alkyl aryl group written as separate word in alphabetically order and adding the words ether at the end. For example, CH3O C2H5 is ethyl methyl ether. If both the alkyl group are the same, the prefix di is added before the alkyl group. For example, C2H5O C2H5 is diethyl ether. According to IUPAC system of nomenclature, ether are regarded as hydrocarbon derivative in which a hydrogen atom is replaced by an OR or OAR group where R and AR represent alkyl and aryl group respectively. The larger group is chosen as the parent hydrogen. The name of a few ether are given as example in table 7.2. Structure of functional group. In alcohols, the oxygen of the OH group is attached to the carbon by a sigma bond formation formed by the overlap of a sp3 hybridized orbital of a carbon with a sp3 hybridized orbital of oxygen. Figure 7.1 depicts structural aspects of methanol, phenol and methoxymethane. The bond angle in alcohol is slightly less than the tetrahedral angle 109 degree to 28 dash. It is due to a repulsion between the unshared electron pair of oxygen. In phenol, the OH group is attached to sp2 hybridized carbon of an aromatic ring. The carbon-oxygen bond length is 136 pm. In phenol is slightly less than that in methanol. This is due to partial double bond character on account of the conjugation of unshared electron pair of oxygen with the aromatic ring. sp2 hybridized state of carbon to which oxygen is attached. In ether, the 4 electron pair, the 2 bond pair and 2 lone pair of electron and on oxygen are arranged approximately in a tetrahedral arrangement. The bond angle is slightly greater than the tetrahedral angle due to the repulsion interaction between the two bulky groups. The CO bond length 141 pm is almost the same as in alcohols. Alcohol and phenols. Preparation of alcohol. Alcohol are prepared by the following method. From alkenes. By acid catalyzed hydration. Alkenes react with water in the presence of acid as catalyst to form alcohol. In case of unsymmetrical alkenes, the addition reaction takes place in accordance with Marconi's Cove rule. Mechanism. The mechanism of the reaction involved the following three steps. Step first, protonation of alkene to form carbocation by electrophilic attack of H3O positive. Step second, nucleophilic attack of water on carbocation. Step 3, deprotonation to form an alcohol. By hydroboration oxidation, diborane react with alkanes to give trialkyl boranes as addition product. This is oxidized to alcohol by hydrogen peroxide in the presence of aqueous sodium hydroxide. The addition of borane to the double bond take place in such a manner that the borane atom get attached to the sp2 carbon carrying greater number of hydrogen atom. The alcohol so formed looks as if it has been formed by the addition of water to the alkene in a way opposite to the Markovnikov's rule. In this reaction, alcohol is obtained in excellent yield from carbonyl compound. By reduction of aldehyde and ketone, aldehyde and ketones are reduced to the corresponding alcohol by addition of hydrogen in the presence of catalyst. The usually catalyst is a finely divided metal such as platinum, palladium and or nickel. It is also prepared by treating aldehydes and ketones with sodium borohydride or lithium aluminum hydride. Aldehyde yield primary alcohol whereas ketones give secondary alcohols by reduction of carboxyl acid and esters. Carboxylic acid are reduced to primary alcohol in excellent yields by lithium aluminum hydride, a strong reducing agent. However, LiAlH4 is an expensive reagent and therefore used for preparing special chemical only. Commercially, acid are reduced to alcohol by converting them to esters, followed by their reduction using hydrogen in the presence of catalyst. From Grignard reagent, alcohol are produced by the reaction of Grignard reagent unit 6 class 12th with aldehyde and ketones. The first step of the reaction is a nucleophilic addition of Grignard reagent to the carbonyl group to form an adduct. Hydrolysis of the adduct yield an alcohol. The overall reaction using different aldehyde and ketones are as follows. You will notice that the reaction produces a primary alcohol with methanol and secondary alcohol with other aldehyde and tertiary alcohol with ketones. Preparation of phenol. Phenol, also known as carboxylic acid, was first isolated in the early 19th century from coal tar. Nowadays, phenol is commercially produced synthetically in the laboratory. Phenols are prepared from benzene derivated by any of the following methods. From haloarenes, chlorobenzene is fused with NaOH at 623 Kelvin and 320 atmospheric pressure. Phenol is obtained by acidification of sodium phenoxide so produced. From benzene sulfonic acid. Benzene is sulfonated with oleum and benzene sulfonic acid so form is converted to sodium phenoxide on heating with molten sodium hydroxide. Acidification of the sodium salt gives phenol. From diazonium salt. A diazonium salt is formed by treating an aromatic primary amine with nitrous acid. Diazonium salt are hydrolysis to phenols by warming with water or by treating with dilute acids. From cumene. Phenol is manufactured from the hydrogen carbon cumene. Cumene is oxidized in the presence of air of cumene hydroperoxides. It is converted to phenol and acetone by treating it with dilute acid. Acetone, a byproduct of this reaction, is also obtained in large quantities by this method. Physical properties. Alcohol and phenol consist of two parts, an alkyl and aryl group and a hydroxyl group. The properties of alcohol and phenol are chiefly due to hydroxyl group. The nature of alkyl and aryl group simply modify these properties. Boiling point. The boiling point of alcohol and phenol increase with increase in the number of carbon atom. In alcohol, the boiling point decrease with increase of branching in carbon chain because of decrease in van der Waals forces with decrease in surface area. The OH group in alcohol and phenol is involved in intermolecular hydrogen bonding as shown below. It is interesting to note that boiling point of alcohol and phenol are higher in comparison to other classes of compound, namely hydrocarbon, ether, haloalkanes, and haloarenes of comparable molecular masses. For example, ethanol and propane have comparable molecular masses, but their boiling point differ widely. The boiling point of methanoxymethane is intermediate of the two boiling points. The high boiling point of alcohol are mainly due to the presence of intermolecular hydrogen bonding in them, which is lacking in ethers and hydrocarbons. Solubility of alcohol and phenol in water is due to their ability to form hydrogen bond with water molecule as shown. The solubility decrease with increase in the size of alkyl aryl group. Several of the lower molecular masses alcohol are miscible with water in all proportions. Chemical reaction. Alcohol are versatile compound. They react both as nucleophiles and electrophiles. The bond between OH is broken when alcohol react as nucleophiles. The bond between CO is broken when they react as electrophiles. Protonation alcohol react in this manner. Based on the cleavage of OH and CO bond, the reaction of alcohol and phenol may be divided into two groups. Reaction involving cleavage of OH bond. Acidity of alcohol and phenols. Reaction with metal. Alcohol and phenols react with active metals such as sodium, potassium, and aluminium to yield corresponding alkoxides and phenoxides and hydrogen. In addition of these, phenol react with aqueous sodium hydroxide to form sodium phenoxides. The above reactions show that alcohol and phenols are acidic in nature. In fact, alcohol and phenol are Bronsted acid. They can donate a proton to a stronger base. Acidity of alcohol. The acidic character of alcohol is due to polar nature of OH bond. In an electron releasing group increases electron density on oxygen tendency to decrease the polarity of OH bond. This decreases the acid strength. For this reason, the acid strength of alcohol decrease in the following order. Alcohol are however weaker acid than water. This can be illustrated by the reaction of water with an alkoxide. This reaction shows that water is a better proton donor than alcohol. Also in the above reaction, we note that an alkoxide ion is a better proton acceptor than hydroxide ion, which suggests that alkoxides are stronger base. Alcohol act as Bronsted bases as well. It is due to the presence of unshared electron pair in oxygen, which make them proton acceptor. Acidity of phenols. The reactions of phenol with metal and sodium hydroxide indicate its acidic nature. The hydroxyl group in phenol is directly attached to the sp2 hybridized carbon of benzene ring, which act as an electron withdrawing group. Due to this, the charge distribution in phenol molecules as depicted in the resonance structures causes of the oxygen of OH group to be positive. The reaction of phenol with aqueous sodium hydroxide indicate that phenol are stronger acid than alcohol and water. Let us examine how a compound in which hydroxyl group attached to an aromatic ring is more acidic than one in which hydroxyl group is attached to an alkyl group. The ionization of an alcohol and a phenol take place as follows. Due to the higher electronegativity of sp2 hybridized carbon of phenol to which OH is attached, electron density decrease on oxygen. This increases the polarity of OH bond and result in an increase in the ionization of phenols than that of alcohol. Now let us examine the stability of alkoxides and phenoxides ions. The alkoxides ion, the negative charge is located on oxygen, while a phenoxide ion, the charge is delocalized. The delocalization of negative charge makes phenoxide ion more stable and favors the ionization of phenol. Although there is also charge delocalization in phenol, its resonance structure have charge separation due to which the phenol molecule is less stable than phenoxide ion. The substituted phenol, the presence of electron withdrawing groups such as nitro group enhances the acidic strength of phenol. This effect is more pronounced when such a group is present as ortho and para position. It is due to the effective delocalization of negative charge in phenoxide ion. When a substituent as at ortho and para position. On the other hand, the electron releasing groups such as alkyl group in general do not favor the formation of phenoxide and resulting in decrease in acidic strength. Cressols, for example, are less acidic than phenols. From the above data, you will note the phenol is millions times more acidic than ethanol. Esterification. Alcohol and phenol react with carboxyl acid, acid chloride, and acid anhydrous to form esters. The reaction with carboxylic acid and acidic acid anhydride is carried out in the presence of a small amount of concentrated sulfuric acid. The reaction is reversible and therefore water is removed as soon as it's formed. The reaction with acid chloride is carried out in the presence of base so as to neutralize HCl which is formed during the reaction. If to shift the equilibrium to the right hand side, the introduction is acetyl group in alcohol or phenol is known as acetylation. Acetylation of salicylic acid produces aspirin. Reaction involving cleavage of carbon-oxygen bond in alcohol. The reaction involving cleavage of CH bond take place only in alcohols. Phenol show this type of reaction only with zinc. Reaction with hydrogen halides. Alcohol react with hydrogen halide to form alkyl halide. The difference in reactivity of three classes of alcohol with HCl distinguish them from one another. Alcohol are soluble in Lucas reagent while their halides are immiscible and produce tuberity in solution. In case of tertiary alcohol, tuberity is produced immediately as they form the halides easily. Primary alcohol do not produce tuberity at room temperature. Reaction with phosphorus trihalides. Alcohol are converted to alkyl bromide by reaction with phosphorus tribromide. Dehydration. Alcohol undergo dehydration to form alkenes on treating with a protic acid. Example concentrated H2SO4 or H3PO4 as catalyst such as anhydrous zinc chloride as alumina. Ethanol undergo dehydration by heating it with concentrated to H2SO4 at 443 Kelvin. Secondary and tertiary alcohol are dehydrated under milder condition. For example, thus the relative ease of dehydration of alcohol follows the following order: tertiary, secondary, primary. The mechanism of dehydration of ethanol involved in the following step. Mechanism: step first, formation of protonated alcohol. Step second, formation of carbocation. It is the slowest step and hence the rate determining step of the reaction. Step 3, formation of ethene by elimination of a proton. The acid used in step 1 is released in the step 3 to derive the equilibrium to the right. Ethene is removed as is it formed. Oxidation. Oxidation of alcohol involves the formation of carbon oxygen double bond with cleavage of an OH and CH bond. Such a cleavage and formation of bond occur in oxidation reaction. These are also known as dehydrogenation reaction as these involve loss of dihydrogen form and alcohol molecules. Depending on the oxidizing agent used as a primary, alcohol is oxidized to an aldehyde which is turned to oxidize to a carboxylic acid. Strong oxidizing agents such as acidified potassium permanganate are used to getting carboxylic acid from alcohol directly. CrO3 in anhydrous medium is used as an oxidizing agent for the isolation of aldehyde. A better reagent of oxidation of primary alcohol to aldehyde in good yield is pyridinium chlorochromate, a complex of chromium trioxide with pyridine and HCl. Secondary alcohol are oxidized to ketone by chromic anhydride CrO3. Tertiary alcohol do not undergo oxidation reaction under strong reaction conditions such as strong oxidizing agent and equivalent temperature. Cleavage of various CC bond take place and a mixture of carboxylic acid containing lesser number of carbon atom is formed. When the vapors of primary or a secondary alcohol are passed over heated copper at 573 Kelvin, dehydrogenation take place and an aldehyde or ketone is formed while tertiary alcohol undergo dehydration. Reaction of phenol. Following reactions are shown by phenols only. Electrophilic aromatic substitution and phenol, the reaction that take place on the aromatic ring, are electrophilic substitution reaction. The OH group attached to the benzene ring activates it toward electrophilic substitution. Also, it directs the incoming group to ortho and para position in the ring, as these positions become electron rich due to the resonance effect caused by OH group. The resonance structure are shown under the acidity of phenol. Common electrophilic aromatic substitution reaction take place in phenol as in follow. Nitration. With dilute nitric acid at low temperature to 98 Kelvin, phenol yields a mixture of ortho and para nitrophenols. The ortho and para isomers can be separated by steam distillation. O nitrophenol is steam volatile due to intermolecular hydrogen bonding, while P nitrophenol is less volatile due to intermolecular hydrogen bonding, which causes the association of molecules. With concentrated nitric acid, phenol is converted to 2,4,6-trinitrophenol. The product is commonly known as pyric acid. The yield of the reaction product is poor. Nowadays, picric acid is prepared by treating phenol first with concentrated sulfuric acid, which converted it to a phenol 2,4-disulfonic acid, and then with concentrated nitric acid to get 2,4,6-trinitrophenol. Can you write the equation of the reaction involved? Halogenation. On treating phenol with bromine, different reaction products are formed under different experimental conditions. When the reaction is carried out in solvent of low polarity such as CHCl3 or CH2, and at low temperature, monobromphenols are formed. The usually hydrogenation of benzene take place in the presence of Lewis acid such as FeBr3, which polarize the halogen molecules. In case of phenol, the polarization of bromine molecule take place even in the absence of Lewis acid. It is due to the highly activating effect of OH group attached to the benzene ring. When phenol is treated with bromine water, 2,4,6-tribromophenol is formed as white precipitate. Kolb's reaction. Phenoxide ion generated by treating phenol with sodium hydroxide is even more reactive than phenol toward electrophilic aromatic substitution. Hence, it undergo electrophilic substitution with carbon dioxide, a weak electrophile. Ortho-hydroxybenzenoic acid is formed as the main reaction product. Riemann-Timmer reaction. On treating phenol with chloroform in the presence of sodium hydroxide, a CHO group is introduced at ortho position of benzene ring. This reaction is known as Riemann-Timmer reaction. The intermediate substituted benzyl chloride is hydrolyzed in the presence of alkyl to produce salicylate. Reaction of phenol with zinc dust. Phenol is converted to benzene on heating with zinc dust. Oxidation. Oxidation of phenol with chromic acid produces a conjugated diacetone known as benzoquinone. In the presence of air, phenol are slowly oxidized to dark colored mixture containing quinones. Some commercial important alcohols, methanol and ethanol, are among the two commercial important alcohol. Methanol. Methanol CH3OH is also known as wood spirit. Was produced by destructive distillation of wood. Today, most of the methanol is produced by catalytic hydrogenation of carbon monoxide at high pressure and temperature, and in the presence of ZNO Cr2O3 catalyst. Methanol is a colorless liquid and boils at 337 Kelvin. It is highly poisonous in nature. Ingestion of even small quantities of methanol can cause blindness, and large quantities cause even death. Methanol is used as a solvent in paints, varnishes, and charcoal for making formaldehyde. Ethanol. C2H5OH is obtained commercially by fermentation. The oldest method is from sugars. The sugar is in molasses. Sugarcane or fruit such as a grape is converted to glucose and fructose in the presence of an enzyme, invertase. Glucose and fructose undergo fermentation in the presence of another enzyme, zymase, which is found in yeast. In wine making, grapes are the source of sugar and yeast. As grapes ripen, the quality of sugar increase and yeast grown in the outer skin. When grapes are crushed, sugar and the enzyme come in the contact and fermentation start. Fermentation take place in the anaerobic condition. In absence of air, carbon dioxide is released during fermentation. The action of zymase is inhibited once the percentage of alcohol formed exceed 40%. If air get into fermentation mixture, the oxygen of air oxidize ethanol to ethanoic acid, which in turn destroys the taste of alcoholic drinks. Ethanol is a colorless liquid with boiling point 351 Kelvin. It is used as a solvent in paint industries and in the preparation of a number of carbon compounds. The commercial alcohol is made unfit for drinking by mixing it some copper sulfate and pyridine. It is also known as denaturation of alcohol. Nowadays, large quantities of ethanol are obtained by hydration of ethene. Ethers, preparation of ether by dehydration of alcohol. Alcohol undergo dehydration in the presence of protic acids. The formation of the reaction product alkane or ether depends on the reaction condition. For example, ethanol is dehydrated to ethene in the presence of sulfuric acid at 443 Kelvin. At 413 Kelvin is the main product. The formation of ether is as nucleophilic bimolecular reaction SN2 involving the attack of alcohol molecule on the protonation of alcohol as indicated below. Acidic dehydration of alcohol is to give an alkene is associated with substitution reaction to give an ether. The method is suitable for the preparation of ether having primary alkyl group only. The alkyl group should be unhindered and the temperature be kept low, otherwise the reaction favors the formation of alkane. The reaction follows SN1 pathway when the alcohol is secondary or tertiary, about which you will learn in higher classes. However, the dehydration of secondary and tertiary alcohol to give corresponding ether is successfully as elimination completes over substitution, and as the consequence alkenes are easily formed. Can you explain why is bimolecular dehydration not appropriate the preparation of ethyl methyl ether? Williamson synthesis. It is an important laboratory method for the preparation of symmetrical and unsymmetrical ethers. In this method, an alkyl halide is allowed to react with the sodium alkoxide. Ether containing substituted alkyl group may be also be prepared by this method. This reaction involves SN2 attack on alkoxide ion on primary alkyl halide. Better results are obtained if the alkyl halide is primary. In case of secondary and tertiary alkyl halide, elimination completes over substitution. If a tertiary alkyl halide is used, an alkene is the only reaction product and no ether is formed. For example, the reaction of CH3ONA with CH3,3CBr gives exclusively 2-methylpropene. It is because are not only nucleophiles but strong base as well. They react with alkyl halide leading to elimination reaction. Phenols are also converted to ether by this method. In this, phenol is used as a phenoxide moiety. Physical properties. The CO bond in ether are polar and thus ether have a net dipole moment. The weak polarity of ether do not appreciably affect their boiling point, which are comparable to those of the alkanes of comparable molecular masses, but they are much lower than the boiling point of alcohol as shown in the following cases. The larger difference in boiling point of alcohol and ethers is due to in the presence of hydrogen bonding in alcohol. The miscibilities of ether with water resemble those of alcohol of a same molecular masses. Both ethoxyethane and butane 1-ol are miscible to almost the same extent, respectively, while pentane is essentially immiscible with water. Can you explain the observation? This is due to the fact that just like alcohol, oxygen of ether can also form hydrogen bond with water and molecule as shown. Chemical reaction. Cleavage of C bond in ethers. Ether are the least reactive of the functional group. The cleavage of CO bond in ether take place under drastic condition with excess of hydrogen halide. The reaction of dialkyl ethers gives to alkyl halide molecule. Alkyl aryl ether are cleaved at the alkyl oxygen bond due to the more stable aryl oxygen bond. This the reaction yield phenol and alkyl halide. Ether with two different alkyl group are also cleaved in the same manner. The order of the reactivity of hydrogen halide is as follows: Hi greater than HBr greater than HCl. The cleavage of ether take place with concentrated Hi or HBr at high temperature. However, when one of the alkyl group is a tertiary group, the halide formed is a tertiary halide. This is because in step 2 of the reaction, the departure of leaving group creates a more stable carbocation and the reaction follows SN1 mechanism. In case of any sol, methyl phenyl oxenium ion is formed by protonation of ether. The bond between OCH3 is weaker than the bond between OC6H5 because the carbon of phenyl group is sp2 hybridized and there a partial double bond character. Therefore, the attached by I negative ions break OCH3 bond to form CH3I phenols. Do not react further to give halide because the sp2 hybridized carbon of phenol cannot undergo nucleophilic substitution reaction needed for conservation of the halide. Electrophilic substitution. The oxy group is ortho-para directing and activate the aromatic ring toward electrophilic substituted in the same way as in phenol. Halogenation. Phenylalkyl ethers undergo usual hydrogenation in the benzene ring. Example, anisole undergoes bromination with bromine in ethanoic acid even in the absence of iron 3 bromide catalyst. It is due to the activation of benzene ring by the methoxy group. Para isomer is obtained in 90% yield. Friedel-Crafts reaction. Anisole undergo Friedel-Crafts reaction. The alkyl and acyl group is introduced at ortho and para position by reaction with alkyl halide and acyl halide in the presence of anhydrous aluminum chloride as catalyst. Nitration. Anisole react with a mixture of concentrated sulfuric and nitric acid to yield a mixture of ortho and para nitro anisole.